Hello everyone, and welcome to Walkthrough 6, Huffin Puff. So in Huffin Puff, what we are doing is going to be dealing with a Huffman compressed file and then puffing it back up, so decompressing it, so that we can translate from the zeros and ones that the user sends us and convert it back into the original text. PSET 6 is going to be pretty cool because you're going to see some of the tools that you used in PSET 4 and PSET 5 and kind of combining them into one pretty neat concept when you come to think about it. Also, arguably, PSET 4 and 5 were kind of the most challenging PSETs that we had to offer. So from now, we have this one more PSET in C, and then after that, we're on to web programming. So congratulate yourselves for kind of getting over the toughest hump in CS50. So moving on for Huffin Puff. Our toolbox for this PSET are going to be Huffman trees, so understanding not only how binary trees work, but also specifically Huffman trees, how they're constructed. And then we're going to have a lot of distribution code in this PSET. And we'll come to see that actually some of the code we might not be able to fully understand yet, and so those will be the .c files, but then their accompanying .h files will give us enough understanding that we need basically so that we know how those functions work, or at least what they're supposed to do, their inputs and outputs, even if we don't know kind of what's happening in the black box or don't understand what's happening in the black box within. And then finally, as usual, we are dealing with new data structures, right? Specific types of nodes that point to certain things. And so here, having a pen and paper, not only for the design process and when you're kind of trying to figure out how your PSET should work, but also during debugging, if you're, you can have GDB alongside your pen and paper while you take down what the values are, where your arrows are pointing, things like that. All right, so first let's look at Huffman trees. So Huffman trees are binary trees, meaning that each node only has 2 children. And so in Huffman trees, the characteristics is that the most frequent values are represented by the fewest bits. We saw in lecture examples of Morse code, which kind of consolidated some letters into basically, if you're trying to translate an A or an E, for example, you're translating that often. So instead of having to use the full set of bits allocated for that usual data type, you compress it down to fewer, and then those letters who are represented less often are represented with longer bits because you can afford that when you weigh out the frequencies that those letters appear. So we have the same idea here in Huffman trees, where we have basically we are basically making a chain, a kind of path to get to the certain characters, and then the characters who have the most frequency are going to be represented with the fewest bits. So the way that you construct a Huffman tree is by looking at by basically placing all of the characters that appear in the text and calculating their frequency, how often they appear. This could either be a count of how many times those letters appear, or perhaps a percentage of how many, basically out of all of the characters, how many each one appears. And so what you do is once you have all of that mapped out, then you look for the 2 lowest frequencies and then join them as siblings, where then the parent node has a frequency which is the sum of its 2 children. And then you, by convention, say that the left node you follow that by following the 0 branch, and then the rightmost node is the 1 branch. And so, as we saw in Morse code, the one gotcha was that, like, for instance, if you had just a beep in the beep, it was ambiguous. It could either be 1 letter, it could be a sequence of 2 letters. And so what Huffman trees does is, because by nature of the characters, or like our final actual characters being the nodes, being the last nodes on the branch, then we refer to those as leaves. By virtue of that, there can't be any ambiguity in terms of which letter you're trying to encode with the series of bits, because nowhere along the bits that represent 1 letter will you encounter like another whole letter, and there won't be any confusion there. But we'll go into examples that you guys can actually see that instead of us just telling you that that's true. Okay, so let's look at a simple example of a Huffman tree. I have a string here that is 12 characters long. I have 4 A's, 6 B's, and 2 C's. So my first step would be to basically count. Okay, well, how many times does A appear? It appears 4 times in the string. B appears 6 times, and C appears 2 times. So naturally, I'm going to say, well, I'm using B most often, so I want to represent B with the fewest number of bits, the fewest number of zeros and ones. And then I'm also going to expect C to require the most amount of zeros and ones as well. So first what I did here is I placed them in ascending order in terms of frequency. So we see that the C and the A, those are our 2 lowest frequencies. So we create a parent node, and that parent node doesn't have a letter associated with it, but it does have a frequency, which is the sum. And so the sum becomes 2 plus 4, which is 6. And so then we follow the left branch. If we were at that 6th node, then we would follow 0 to get to C, and then 1 to get to A. So now we have 2 nodes. We have 6. We have the value 6, and then we also have another node with the value 6. And so those 2 are not only the 2 lowest, but also just the 2 that are left. So we join those by another parent, with the sum being 12, and so here we have our Huffman tree, where to get to B, that would just be the bit 1, and then to get to A, we would have 0, 1, and then C having 0, 0. And so here we see that basically we're representing these chars with either 1 or 2 bits, where the B, as predicted, has the least. And then we had expected C to have the most, but since it's such a small Huffman tree, then the A is also represented by 2 bits as opposed to like somewhere in the middle. All right, so just to go over another simple example of a Huffman tree. Say you have the string hello. What you do is, first you would say, okay, well, how many times does H appear in this? Well, H appears once, right? And then E appears once, and then we have L appearing twice, and O appearing once. And so then we expect which letter to be represented by the least number of bits. L, yeah. L is right. We expect L to be represented by the least number of bits because L is basically used most in this string hello. Okay, so what I'm going to do now is basically draw out these nodes. So I have 1, which is H, and then another 1, which is E, and then a 1, which is O. Right now I'm putting them in order, and then 2, which is L. Okay? And so then I say, okay, well, the way that I build a Huffman tree is to find the 2 nodes with the least frequencies and join them to make make them siblings by creating a parent node. Now here we have actually 3 nodes with the lowest frequency. They're all 1. And so here basically we choose basically which one we're going to link first. So let's say I choose the H and the E, then the sum of 1 plus 1 is 2, but this node doesn't have a letter associated with it, it just holds the value. Now we look at the next lowest. Now we look at the next 2 lowest frequencies. That's 2 and 1. That could be either of those 2, but I'm going to choose this one. The sum is 3, and then finally I only have 2 left. So then that becomes 5. And then here, as expected, if I fill in basically the encoding for that, 1s are always the right branch and 0s are the left one. Okay, so then we have L represented by just 1 bit, and then the O by 2, and then the E by 2, and then the H falls down to 3 bits. Okay. Now, so basically you can transmit this message, hello, instead of actually using the characters by just 0s and 1s. However, remember that we had, in several cases, we basically had ties, right? With our frequency, we could have either joined the H and the O first, maybe, or then later on when we had the L represented by 2 as well as the joined one represented by 2, we could have linked either one. And so basically when you send the zeros and ones, that actually doesn't guarantee that the recipient can fully read your message right off the bat, because they might not know, well, which decision did you make? And so when we're dealing with Huffman compression, then somehow we have to basically tell the recipient of our message how we decided to, basically they need to know some kind of extra information in addition to the compressed message. They need to understand basically what the tree actually looks like, to like how we actually made those decisions. Now here we were just doing examples based on the actual count, but sometimes you can also have a Huffman tree based on the frequency at which letters appear, and it's the exact same process. So here I'm expressing it in terms of like percentages or a fraction, and so here the exact same thing. I find the two lowest, sum them, the next two lowest, sum them until I have a full tree. Now, even though we could do it either way, when we're dealing with like percentages, that means that we're dividing things and dealing with decimals, or rather floats if we're thinking about data structures up ahead. And so what do we know about floats? What's a common problem when we're dealing with floats? Yeah, imprecision. So because of floating point imprecision, for this p set, basically so that we make sure that we don't lose any values, then we're actually going to be dealing with the count. So if you were to think of a Huffman node, if you look back to the structure here, basically it has if you look at the green ones, it has a frequency associated with it, as well as basically it points to a node to its left as well as a node to its right. And then the red ones there also have a character associated with them. We're not going to make separate ones for like the parents and then the final nodes, which we refer to as leaves, but rather basically those will just have null values. So we have, for every node, we'll have a character representing, you know, the symbol that that node represents. Then a frequency, as well as a pointer to its left child as well as its right child. So the leaves, which are at the very bottom, they would also have node pointers to their left and to their right, but since those values aren't pointing to actual nodes, then what would their value be? Null, exactly. And so here's an example of how you might represent the frequency in floats, but we're going to be dealing with it with integer. So all I did is change the data type there. Okay, so let's go on to a little bit of more of a complex example, but now that we've done the simple ones, it's just the same process. You find the two lowest, and then you find the two lowest frequencies, sum them to make a parent, sum the frequencies, and that's the new frequency of your parent node, which then points to its left with the 0 branch and the right with the 1 branch. So if we have the string, this is CS50, then we count, well, how many times is T mentioned, H mentioned, I, S, C, 5, 0. And so then what I did here is with the red nodes, basically I just planted and said, okay, I'm going to have these characters I know eventually at the bottom of my tree. Those are going to be all of the leaves. Then what I did is I sorted them by frequency in ascending order, and this is actually what the way that the p set code does it, is it sorts it by frequency and then alphabetically. So it has the numbers first and then alphabetically by the frequency. So then what I would do is I would find the two lowest, well, that's 0 and 5, and I would sum them, and that's 2, and then I would continue, find the next two lowest, those are the two ones, and then those become 2 as well. Now I know that my next step is going to be joining, well, the lowest number, which is the T, right, the 1, and then basically choosing one of the nodes that has 2 as the frequency, right? So here we have 3 options. What I'm going to do for the slide is just kind of visually rearrange them for you so that you can see how I'm building it up. And so basically what the code in your distribution code is going to do would join the T one with the 0 and 5 node. So then that sums to 3, and then we continue the process. The 2 and the 2 now are the lowest, so then those sum to 4. Everyone following so far? Okay. And then after that, we have the 3 and the 3 that need to be added up. So again, I'm just switching it so that you can see visually so that it doesn't get too messy. Then we have a 6, and then our final step is now that we only have 2 nodes, we sum those to basically make the root of our tree, which is 10. And the number 10 makes sense because each node represented like their value, their frequency number was basically how many times they appeared in the string, and then we have 5 characters in our string, so that makes sense. Okay, so then if we look up at how we would actually encode it, then as expected, the I and the S, which appear the most often, are represented by the fewest number of bits. Now be careful here. When you're making a, in Huffman trees, the case actually matters. So an uppercase S is different than a lowercase s. So if we had actually, this is CS50 with capital letters, then the lowercase s would only appear twice, would be a node with 2 in it as its value, and then uppercase S would only be 1. So then your tree would change structures because you actually have an extra leaf here, but the sum would still be 10. And so that's what we're actually going to be calling the checksum, basically, the addition of all of the counts. Okay, so now that we've covered Huffman trees, then we can dive into Huffin Puff, the P set. So we're going to start with a section of questions, and this is going to get you accustomed with binary trees and how to operate around that, drawing nodes, seeing how, basically creating your own type def struct for a node, and seeing how you might insert into a binary tree, one that's sorted, traversing it, things like that. So that's definitely going to help you, that knowledge, when you dive into the Huffin Puff portion of the P set. So in the standard edition of the P set, your task is to implement puff. And in the hacker version, your task is to implement huff. So what huff does is it takes text and then it translates it into the zeros and ones. So basically the process that we did above, where we counted the frequencies and then basically made the tree and then said, okay, well, if t, how do I get t? Well, t is represented by like 1, 0, 0, things like that. And then so basically Huff would take the text and then output that binary, but also because we know that we want to translate, we want to allow our recipient of the message to recreate the exact same tree, also includes information about the frequency counts. And so then puff, basically we are given a binary file of zeros and ones, and given also the information about the frequencies, we translate all of those zeros and ones back into the original message that was. So we're decompressing that. And so because we're not, if you're doing the standard edition, you don't need to implement Huff, so then you can just use the staff implementation of Huff. There are instructions in the spec on how to do that. So you can run the staff implementation of Huff upon a certain text file, and then use that output as your input to Puff. Okay, so as I mentioned before, we have a lot of distribution code for this one. And so I'm going to start going through it. I'm going to spend most time on the .h files, because in the .c files, because we have the .h and basically that provides us with the prototypes of the functions, we don't fully need to understand exactly, if you don't understand what's going on in the .c files, then don't worry too much, but definitely try to take a look, because it might give some hints, and it's useful to get used to reading other people's code. Okay, so looking at huffile.h, this, as in the comments, it declares a layer of abstraction for Huffman coded files. So if we go down, then we see that there are basically a maximum of 256 symbols that we might need codes for. So there are a maximum of 256 symbols that we might need codes for. This includes all of the letters of the alphabet, uppercase and lowercase, and then symbols and numbers, etc. Then here we have a magic number identifying a Huffman coded file. Basically, within a Huffman code, they're going to have a certain magic number associated with the header. Now, this might look like just a random magic number, but if you actually translate it into ASCII, then it actually spells out Huff. Then here we have a struct for a Huffman encoded file. So there's all of these characteristics associated with a Huff file. And then down here we have a Huff. It's the header for a Huff file, so that we call it Huffheader instead of adding the extra H because it just sounds the same anyway. Cute. Anyway, so we have a magic number associated with it. So that's basically, if it's an actual Huff file, it's going to be the number up above, that this magic one. Okay, and then it'll have an array. So for each symbol, of which there are 256, it's going to list what the frequency of those symbols are within the Huff file. And then finally, we have a checksum for the frequencies, which should be basically the sum of those frequencies. So that's what a Huff header is. All right, and then we have some functions that return the next bit in the Huff file, as well as writes a bit to the Huff file, and then this function here, hfclose, that actually closes the Huff file. Before, we were dealing with straight just fclose, but actually, when you have a Huff file, instead of fclosing it, what you're actually going to do is hfclose and hfopen it. So those are specific functions to the Huff files that we're going to be dealing with. And then here we read in the header and then write a header. So here just by reading the .h file, we can kind of get a sense of what a Huff file might be, what characteristics it has, without actually going into the huffile.c, which, if we dive in, is going to be a bit more complex. So it actually has, all of the file I/O here, dealing with pointers. Here we see that, when we call like hfread, for instance, it's still dealing with fread. We're not getting rid of those functions entirely, but we're kind of sending those to be taken care of inside the Huff file, instead of doing all of it ourselves. So you can feel free to scan through this if you're curious and kind of understand, go on to peel the layer back a little bit. Okay, so the next file that we're going to look at is tree.h. And so before in the walkthrough slides, we said, okay, well, we expect a Huffman node, and we made a typedef struct node. We expect it to have a symbol, a frequency, and then 2 node stars. In this case, what we're doing is this is essentially the same, except instead of node, we're actually going to call them trees. Then we have a function that when you call make tree, it returns you a tree pointer. So back to Speller, when you were making nodes when you're making a new node, you actually said, okay, node star, like new word, for instance, equals malloc, size of, and things like that. And so basically make tree is going to be dealing with that for you. Then similarly, when you want to remove a tree, so that's essentially like freeing the tree when you're done with it, then instead of actually explicitly calling free on that, you're actually just going to use the function remove tree, where you pass in the pointer to that tree, and then tree.c will take care of that for you. So we look into tree.c, we expect the same functions, except to see the implementation as well. So as we expected, when you call make tree, it mallocs the size of a tree into a pointer initializes all of the values to like the null values, so zeros or nulls, and then returns the pointer to that tree that you've just malloced to you. And then here, when you call remove tree, first make sure that you're not double freeing, so make sure that you actually have a tree that you want to remove. And so here, because a tree also includes its children, what this does is it recursively calls remove tree on the left node of the tree as well as the right node. So it frees, before it frees, the parent needs to free the children as well. So then parent is also interchangeable with root, basically the first ever parent, so like the great-great-great-great-grandfather or grandmother tree. First we have to free down the levels first, so traverse to the bottom, free those, and then come back up, free those, etc. Okay, so that's tree. Now we look at forest. So forest basically is where you place all of your Huffman trees. So it's saying that we're going to have something called a plot that contains a pointer to a tree as well as a pointer to a plot called next. So what does this remind, what structure does this kind of look like? Kind of says it over there, right over here. A linked list, right? So we see that it looks like when we have a plot, it's like a linked list of like plots. And so here, when we basically a forest is defined as a linked list of plots, and so the structure for a forest is basically we're just going to have a pointer to our first plot, and then that plot has a tree within it, or rather points to a tree and then points to the next plot, so on and so forth. So then we have, to make a forest, we call make forest. Then we have some pretty useful functions here. So we have pick, where you pass in a forest, and then the return value is a tree star, a pointer to a tree. So what pick will do is it'll go into the forest that you're pointing to, then basically remove a tree with the lowest frequency from that forest, and then give you the pointer to that tree. So the tree, once you call pick, the tree won't exist in the forest anymore, but the return value is that tree, is the pointer to that tree. Then you have plant. So provided that you pass in a pointer to a tree that has a non-zero frequency, then what plant will do is it'll take the forest, take the tree, and plant that tree inside of the forest. Then here we have remove forest. So similar to remove tree, which basically freed all of our trees for us, then remove forest will free everything contained in that forest. So if we look into forest.c, then we'll expect to see a couple of remove tree. We'll expect to see at least one remove tree command in there, right? Because to free memory in the forest, if it consists of, if a forest has trees in it, then eventually you're going to have to remove those trees too. So if we look into forest.c, we have our make forest, which is as we expect, we malloc things. We initialize the first first plot in the forest. It's null because it's empty to begin with. Then we see pick, which returns the tree with the lowest weight, the lowest frequency, and then basically gets rid of that particular node that points to that tree and the next one. So it takes that out of the linked list of the forest. And then here we have plant, which basically inserts a tree into the linked list. Keeps what forest does, it nicely keeps it sorted for us. And then finally we have remove forest, and as expected we have remove tree called there. Okay. So looking at the distribution code so far, huffile.c was probably by far the most probably the hardest to understand, whereas the other files themselves were pretty simple to follow. With our knowledge of pointers and linked lists and such, we were able to follow pretty well. But all we need to really make sure that we fully understand is the .h files, because you need to be calling those functions, dealing with those return values. So make sure that you fully understand what action is going to be performed whenever you call one of those functions. And then, but actually understanding inside of it isn't quite necessary because we have those .h files. Okay, so we have 2 more files left in our distribution code. Let's look at dump. So dump, by its comment here, takes a Huffman compressed file and then basically translates and dumps all of its content out. So here we see that basically it's calling HF open. So instead, this is kind of mirroring to a file star, like input equals f open, and then you pass in the information. It's almost identical, except instead of a file star, you're passing in a Huff file. Instead of f open, you're passing in HF open. Okay, so then here we read in the header first, which is kind of similar to how we read in the header for an RGB, for a bitmap file. And so then what we're doing here is checking to see whether the header information contains the right magic number that indicates that it's an actual Huff file. Then basically all of these checks to make sure that the file that we open is an actual Huffed file or not. Then what this does is it basically outputs the frequencies of all of this of all of the symbols that we can actually see within a terminal into a graphical table. And then what this does is this part is going to be useful, is it has a bit and basically reads bit by bit into the variable bit and then prints it out. So if I were to call dump on hth.binary, which is basically the result of huffing a file using the staff solution, then I would get this. So it's outputting all of these characters and then putting the frequency at which they appear. And so if we look, most of them are zeros except for this. H, which appears twice, and then T, which appears once. And then here we have a here we have basically the actual message in zeros and ones. And so if we look at hth.text, which is presumably the original message that was huffed, then we expect to see some H's and T's in there. Specifically, we expect to see just 1 T and 2 H's. And here we are in hth.text. It indeed has hth. And then included in there, although we can't see it, is actually a new line character. And so the Huff file hth.bin is also kind of encoding the new line character as well. So here, because we know that the order is HTH and then new line, we can see that probably the H is represented by just a single 1, right? And then the T is probably 0, 1, and then the next H is 1 as well, and then we have a new line indicated by 2 zeros. Cool. And then finally, because we're dealing with multiple .c and .h files, then we're going to have a pretty complex argument to the compiler. And so here we have a make file that makes dump for you, but actually you have to go about making your own puff.c file. So the make file actually doesn't deal with making puff huffpuff.c for you. So we're leaving that up to you to edit the make file to basically when you enter a command like make all, for instance, it will make all of them for you. Feel free to look at the examples of make file from the past pset for, and as well as going off of this one to see how you might be able to make your puff file by editing this make file. So that's about it for our distribution code. And so once we've gotten through that, then here's just another reminder of basically how we're going to be dealing with the Huffman nodes. We're not going to be calling them nodes anymore. We're going to be calling them trees, where we're going to be representing their symbol with a char, their frequency, basically the number of occurrences with an integer. And so we're using that because it's going to be more precise than a float. And then we have another pointer to the left child as well as the right child. Okay. And then a forest, as we saw, is just basically a linked list of trees. And so ultimately, when we're building up our Huff file, we want our forest to contain just one tree, right? One tree, one root with multiple children. So then when we made earlier on when we were just making our Huffman trees, then we started out by placing all of the nodes onto our screen and saying, okay, we're going to have these nodes. Eventually, they're going to be the leaves, and this is their symbol. This is their frequency. So basically, that's in our forest. That's if we just have 3 letters, then that's basically a forest of 3 trees. And then as we go on, when we added the first parent, we made a forest of 2 trees. So we removed 2 of those children from our forest and then replaced it with a parent node that had those 2 nodes as children. Okay, and then finally, our last step with making our example with the A's, B's, and C's would be to make the final parent, right? And so then that would bring our total count of trees in the forest to 1. All right, does everyone see how you start out with multiple trees in your forest and end up with 1? Okay, cool. All right. So what do we need to do for Puff? Well, what we need to do is we need to ensure that, as always, that they give us the right type of input so that we can actually run the program. In this case, they're going to be giving us, after their first command line argument, 2 more, basically the file that we want to decompress, and then basically the output of the decompressed file. But we also want to make sure, once we make sure that they pass us in the right amount of values, is we want to ensure that the input is actually a Huff file or not. And then once we guarantee that it's a Huff file, then we want to build our tree, basically build up the tree such that it matches the tree that the person who sent the message built. Then after we build the tree, then we can deal with the 0s and 1s that they passed in, follow those along our tree because it's identical, and then write that message out, interpret the bits back into chars. And at the end, because we're dealing with pointers here, we want to make sure that we don't have any memory leaks and that we free everything. Okay. So ensuring proper usage is old hat for us by now. We take in an input, which is going to be the name of the file to Puff, and then we specify an output, so the name of the file for the puffed output, which will be the text file. Okay. So that's usage, and now we want to ensure that the input is huffed or not. So thinking back, was there anything in the distribution code that might help us with, understanding whether a file is huffed or not? Well, there was information in huffile.c about the huff header, and so we know that basically every Huff file has a Huff header associated with it with a magic number as well as an array of the frequencies for each symbol as well as a checksum. So we know that, but we also took a peek at dump.c, in which it was dealing and reading and writing in, it was reading into a Huff file. And so to do that, it had to check whether it was a Huff file, whether it really was Huffed or not, right? So perhaps we could use dump.c as a kind of, as a structure for our puff.c. So back to pset 4, when we had the file copy.c that copied in RGB triples, and we interpreted that for whodunit and resize. Similarly, what you could do is just run the command like cp dump.c puff.c and use that and use some of the code there. However, it's not going to be as straightforward of a process for like translating your dump.c into puff.c, but at least it gives you somewhere to start, right, on how to ensure that the input is actually huffed or not, as well as a few other things. Okay, so we have ensured proper usage and ensured that the input is huffed. Every time that we've done that, we have done our proper error checking, so essentially returning and quitting the function if some failure occurs, if there's a problem. Okay, so now what we would want to do is build the actual tree. So if we look in Forest, then there are two main functions that we're going to want to become very familiar with. There's the Boolean function plant that plants a non-zero frequency tree inside our forest. And so there you pass in a pointer to a forest and a pointer to a tree. To be able to point in and so quick question, how many forests will you have in this, like when you're building a Huffman tree? Our forest is like our canvas, right? So we are only going to have one forest, but we're going to have multiple trees. So before you call plant, then you're presumably going to want to make your forest, right? And so there is a command for that if you look into forest.h on basically how you can make a forest. Okay, so then once you can plant a tree, so we know how to do that, and then you can also pick a tree from the forest. So removing a tree with the lowest weight and giving you the pointer to that. So thinking back to when we were like just doing the examples ourselves, we kind of, when we were drawing it out, we simply just added the links, but here, instead of just adding the links, then think of it more as you're removing two of those nodes and then replacing it by another one. So then to express that in terms of picking and planting, then you're picking two trees and then planting another tree that has those two trees that you picked as children. Okay, so then to build Huffman's tree, basically you can read in the symbols and frequencies in order, because the Huff header gives that to you. It gives you an array of the frequencies, and so you can go ahead and just ignore anything with the 0 in it, because we don't want 256 leaves at the end of it. We only want the number of leaves that are actually like characters that are actually used in the file. So then once you can read in those symbols, and basically each of those symbols that have non-zero frequencies, well, those are going to be trees. So what you can do is every time you like basically read in a non-zero frequency symbol, then you can plant that tree in the forest. Then once you plant the trees in the forest, you can join those trees as siblings. So going back to planting and picking, where you pick two and then plant one, where that one that you plant is the parent of the two children that you picked. And so then your end result is going to be a single tree in your forest. Okay. All right, so that's how you build your tree. Now there are several things that could go wrong here, because we're dealing with making new trees and dealing with pointers and things like that. So we want to make sure that whenever, before when we were dealing with pointers, whenever we malloc, we wanted to make sure, right, that it didn't return us a null pointer value. So at several steps within this process, there are going to be like several cases where your program could fail. And so what you want to do is you want to make sure that you handle those errors, and in the spec it says to handle them gracefully. So like print out a message to the user telling them why the program has to quit, and then promptly quit it. And so to do this error handling, remember that you want to check it basically every single time that there could be a failure. Every single time that you're like making a new pointer, you want to make sure that that's successful. Before, what we used to do is we used to make a new pointer and malloc it, and then we would check whether that pointer is null. So there are going to be some instances where you can just do that, but sometimes you're actually calling a function, and within that function, that's the one that's doing the mallocing. So in that case, if we look back to some of the functions within the code, then some of them are actually Boolean functions. So if we have in the abstract case, if we have a Boolean function called foo, then what we could do, basically we can assume that in addition to doing whatever foo does, since it's a Boolean function, it returns true or false. True if successful, false if not. And so basically we want to check whether the return value of foo is true or false. If it's false, then that means that we're going to want to print some kind of message and then quit the program, right? So what we want to do is we want to check the return value of foo. So basically, if foo returns false, then we know that we encountered some kind of error and we need to quit our program. So a way to do this is actually basically have just a condition where the actual function itself is your condition. So say foo takes in x, so we can have as condition if foo x. Basically that means if the result of, if at the end of executing foo it returns true, then we can do this. Because the function essentially has to evaluate foo in order to evaluate the whole condition, right? So then that's how you basically can do something if the function returns true and is like successful. But when you're error checking, you only want to quit if your function returns false, right? So then what you could do is just add an equals equals false, or just add a bang in front of it. And then you have if, like bang foo. So then that would basically, within that body of that condition, then you would basically have all of the error handling, right? So, like could not create this tree, and then return 1 or something like that. And so then what that does though is that even though foo like returned false, so say foo returns true though, then you don't have to like call foo again. That's a common misconception. So even because it was in your condition, it's already evaluated. So you already have the result if you're using like make tree or something like that, or like plant or pick or something. It already has that value. It's already executed. So it's useful to use Boolean functions as the condition, because whether or not you actually execute the body of the loop, it executes the function anyway. Okay, so then our second to last step is actually writing the message to the file. So once we build the Huffman tree, then writing the message to the file is pretty straightforward. So then it's pretty straightforward now to basically just follow the zeros and ones. And so by convention, we know that in a Huffman tree, that the zeros are basically indicate left and the ones indicate right? So then if you read in bit by bit, then every time that you get a 0, then you'll basically follow the left branch. And then every time you read in a 1, then you're going to follow the right branch, right? And then you're going to continue until you hit the until you hit a leaf, right? Because the leaves are going to be at the end of the branches. What characteristic, basically how can we tell whether we've hit a leaf or not? We've said it before. Yeah, we can tell if we've hit a leaf if the pointers to both the left and right trees are null. Perfect. Okay, so we know that we want to basically read in bit by bit into our Huff file. Now, as we saw before in dump.c, what they did is they read in bit by bit into the Huff file and just basically printed out what those bits were. So we're not going to be doing that. We're going to be doing something that's a bit more complex. But what we can do is we can take that bit of code that basically reads into the bit. So here we have the integer bit representing the current bit that we're on. And so this takes care of basically iterating all of the bits in the file until you hit the end of the file. So then based on that, then you're going to want to have some kind of, like basically some kind of iterator, right, to traverse your tree. And then based on whether the bit is 0 or 1, you're going to want to either move that iterator to the left or move it to the right, all the way until you hit a leaf. So all the way until your, like that node that you're on doesn't point to any more nodes. And so why can we do this with a Huffman file but not Morse code? Well, because in Morse code there's a bit of ambiguity, right? We could be like, oh wait, we've hit a letter along the way, right? So maybe this is our letter. Whereas if we continued just a bit longer, then we would have hit another letter. But that's not going to happen in Huffman encoding. So we can rest assured that basically the only way that we're going to hit a character is if that node's left and right children are null. Okay. And then finally, we want to free all of our memory. So we want to both close the Huff file that we've been dealing with, as well as remove all of the trees in our forest. So based on your implementation, you're probably going to want to call remove forest instead of actually going through all of the trees yourself. But if you made any temporary trees, then you'll want to free that. You know your code best, so you know where you're basically allocating memory. And so, like, if you go in, start by even control Fing for malloc, seeing whenever you malloc and making sure that you free all of that. But then just going through your code, understanding where you might have allocated memory. So usually, you might just say, okay, well, at the end of a file, I'm just going to remove forest on my forest. So basically, clear that memory, free that, and then I'm also going to close the file. And then my program's going to quit. But is that the only time that your program quits? No, because sometimes there might have been an error that happened, right? Maybe we couldn't open a file, or we couldn't make another tree, or or some kind of error happened in the memory allocation process, and so it returned null, and then our program printed out an error happened, and then we returned and quit. And so then what you want to make sure is that basically any possible time that your program can quit, you want to free all of your memory there. So it's not just going to be at the very end of the main function that you quit your code. You want to look back to basically every instance that your code potentially might return prematurely, and then free all of the memory, free whatever memory makes sense, right? If at a certain, say you had called make forest and that returned false, then you probably won't need to remove your forest, right? Because you don't have a forest yet. But basically at every point in the code where you might return prematurely, you want to make sure that you free any possible memory. So when we're dealing with freeing memory and having potential leaks, then we want to not only use our judgment and our logic, but also use valgrind, right, to determine whether we've freed all of our memory properly or not. So you can either run valgrind on a puff, and then you have to also pass it the right number of command line arguments to valgrind. So you can run that, but the output is a bit cryptic. We've gotten a bit used to it with Speller, but we still need a bit more help. So then running it with a few more flags, like the leak check full, then that'll probably give us some more helpful output on valgrind. Then another useful tip when you're debugging is the diff command. So basically you can access the staff's implementation of Huff, right? Run that on a text file and then output it to a binary file, a binary Huff file to be specific. Then if you run your own puff on that binary file, then ideally your outputted text file is going to be identical to the original one that you passed in. Here I'm using like hth.txt as the example, right? And that's going to that's the one talked about in your spec. So basically that's just a simple, literally just hth and then a new line, right? But you are definitely feel free and definitely encouraged to use maybe a bit more, use longer examples for your text file. You can even take a shot at maybe compressing or compressing and then decompressing some of the files that you used in spellers, just like War and Peace or Jane Austen or something like that. That would be kind of cool, or like Austin Powers. So kind of dealing with larger files. Because we wouldn't come down to it if we use the next tool here, ls-l. So we're used to ls, right, which basically lists all the contents in our current directory. Well, passing in the flag -l actually displays the size of those files. So if you go through the pset spec, it actually walks you through, creating the binary file of huffing it. And then you see that for very small files, the cost and basically the space cost of compressing it and translating all of that information of all the frequencies and things like that outweighs the actual benefit of actually compressing the file in the first place. But if you run it on some longer text files, then you might see that actually you start to get some benefit actually in compressing those files. And then finally we have our old pal GDB, which is definitely going to come in handy too. All right, do we have any questions on Huff trees or the process perhaps of making the trees, or any other questions on Huffin Puff? Okay, I'll stay around for a bit. Thanks everyone. This was walkthrough 6 and good luck.